Kann ich? It's okay. Okay, then hello everyone. Welcome to my talk. My name is Thorsten Holz, and I'm going to talk in the next hour about anti-honeypot techniques. Okay. So at first I want to give a brief overview of my talk. At first I want to give a very brief introduction into honeypot related technology. Joel, can you? Okay, thanks. Okay, at first I want to give a brief introduction into honeypot related technology. For all of you who haven't seen a talk of Lance Spitzner or similar people from the HoneyNet project, I just want to give probably 15 or 20 minutes, just a brief introduction, so that everyone knows what a honeypot is. Afterwards, I'll talk about our work called Nosebreak. It's about detecting and circumventing and disabling CBAC, the main logging tool that's used to count honeypots. And afterwards, if time permits, I also want to give a short introduction into other anti-honeypot related technologies. Okay, at first a brief overview who I am, or who we are. I'm a member of the Laboratory for Dependable Distributed Systems. If you attended several talks today and yesterday, probably you've seen someone of us already. I think we've got a total of 7 talks or so here. We are a laboratory at the Technical University in Aachen. I'm there a diploma student. I'm currently graduating. I think I'll finish next year in summer or so. The main interests of our lab are, on the one hand side, the theoretical considerations of dependable systems, more from a mathematical point of view, with safety, liveness, and information flow properties, and the modeling of how dependable systems could look like. On the other hand, we also do more practical kind of things about measuring security threats. Therefore, we also run a honeypot, for example. I think 2 hours ago, Maximilian and Michael gave a talk about the security of FireWire, hacking with fire. Probably some of you already seen this talk. And trusted computing, that's the third big part of our research. Probably we have started some more research in this area in the next few months. Then we have some events, the summer school. I also wrote an article for the last issue of the Datenschleuder about this. This was a 3-week intensive course. We had in the morning lectures about sniffing, spoofing, wireless security, forensics, buffer overflows and all this kind of stuff. And in the afternoon there were more practical exercises. The people had to program their buffer overflows, war driving, and sniffing in wireless or in switch networks. These were the topics. It was very interesting. Probably we also go to do this again next fall, probably only 2 weeks. So if someone is interested in this, you should contact me. We are currently preparing everything, and there will be a summer school again. We all have, during the semester, we have several other events, for example, Hacking Lab and the Hacker Seminar, with all the topics that are also covered at these lectures at 21C3. At the webpage, you can find more information about us. Okay, at first a small picture about the basic idea behind honeypots. So you want to learn something about attackers, about hackers, crackers, and other people who do funny things in the wild. And of course you have to give them something. You have to give them some kind of decoy to lure in them, and then you can study them. It's depicted on the picture. Probably as a child you read this. Okay, as I said before, honeypots are mostly electronic baits. So like a decoy in the real world, we have decoys in the electronic world. In our area, these are normal computers, routers, switches. We also have some printers as honeypots, and these are just toys, and the attackers, they are lured in. We also modify these tools so that they log everything, what's going on. That helps us basically in forensics afterwards. The motto of the HoneyNet project is to learn the tools, tactics, and motives of the Black Hat community. You can read it everywhere on the HoneyNet, on the official HoneyNet site. If you've seen a talk of Lance Spitzner, he probably says it 20 times or so, and this is the basic idea behind the whole project. The main idea is very old. Back in 1988, Clifford Stoll, who was an administrator of a research network, he used the idea of decoys. He learned there was an attacker inside his network. He gave him more and more entrance to his own network, and he was able to trace him down. And actually, he was able to trace him down. The guy that was someone of the, Hannover, so a German hacker. He was able to trace him. There's a similar approach, and also another paper that's from 1989 from Bill Cheswick, who also describes how he studied an attacker and how he used honeypots. In the recent years, the interest in honeypots grew more and more, mainly because of Lance Spitzner and the official Honeynet project now. So the ideas are old, but in the last few years there was some kind of hype, and probably it's worth it because honeypots are a useful tool in my eyes. The Honeynet project itself, it's a research organization, it's worldwide. Currently there are 20 members. At the laboratory at our university, we are the official German Honeynet project. There are also the French Honeynet project in UK, in Greece, in Norway, and then there are many American university and other researchers who run their own honeypot, and they are all members of the Research Alliance. To be a member in the Research Alliance just means that you work together with those people. We have an internal mailing list. We coordinate what we do. We write papers about our findings and this kind of stuff. You can find the official page at honeynet.org. And there you can also read about the experience that the members had up to now. For example, probably one of the most exciting ones was the capturing of an exploit. The vulnerability was known before, but there was no exploit known, and with the help of honeypot there was someone who could catch the actual exploit. Last year a similar example was also found by one other person. Honeypots also help to learn more about the tools that attackers use. For example, if you run a honeypot, somebody breaks in and compromises your systems, you have, via all the logging that's done, you get the tools, and you also see what techniques he used. You also got something of the motives. If you just take a look at their IRC what they talk about in IRC, what they mail, and what they do once they compromise your honeypot. There are several papers about these motives. For example, if with the help of a honeypot there was a botnet with about 15,000 hosts that was found. Within this network there was an automated credit card trading. So there were some carders who were trading those credit cards, some bots who were validating the numbers and this kind of stuff. And for the information, just go to the official site and take a look at the papers that are online. To understand how a honeypot looks like, we just take a look at the building blocks. There are just a few building blocks, and if you combine these together, you've got your own honeypot. The first building block is CBAC. CBAC is the main tool that's currently used by Honeynet researchers. It is used for logging. It basically just hijacks the system read call, and by doing this, it's able to log everything. For example, it can log SSH connections. If you copy something via SCP on a honeypot, you can monitor this. Or if the binary is protected with BurnEye or similar tools, I get the password and I can decrypt it afterwards. More on CBAC I'll talk about later because Nosebreak, so our main project, is based on exploiting what CBAC does. The second basic block is the so-called honey wall. It's mainly used for data capture and data control. Data capture just means that you log everything. So you've got just TCP dump or TLReal or your favorite tool running on the honey wall. It captures everything, writes it to files for later analysis. And the other thing is data control, because this is mainly for legal issues. If someone compromises one of your honeypots, you've got the problem that he could also compromise other machines. Probably you don't want to harm other people, so you have to ensure that if someone compromises one of your honeypots, he can't harm other people's. Via data control, you can do this. For example, you can do some rate limiting to prevent denial of service attacks against other machines, or you can only rate limit that only, for example, 15 outgoing TCP connections per day are allowed. This is enough if someone compromises your honeypot, that he can download his tools, but he can't harm other people that easy. And the other thing that is normally installed is the so-called snort inline. Snort inline, an intrusion prevention system. We use it more or less like an extrusion prevention system. So we stop exploits that are originating from one of the honeypots to other machines. For this to work, we have here, for example, this rule. This rule says that if the content of a packet has this EB02, 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 then we just want to replace this with just crap, so that the exploit that's originating from one of the honeypots to another host, that it fails. We just log it and no other system should be harmed. Apart from replacing, you can also drop the packets, and so you can just also stop if your replacing isn't enough for you, then you just drop the packet, and yeah, basically no one can exploit, with known exploits, of course, other machines. Yeah, I said before, netfilter IP tables for traffic limiting. We use, for example, about 20 outgoing TCP connections, I think 30 outgoing UDP connections, then some ping, and the rest is about also 30 other connections, so that they don't tunnel via fancy protocols outside. Yeah, and other things that are running on the Honeywall are mostly for supervision. So, for example, supervise or monitor to ensure that TCP dump and all other tools are running, and we use Swatch for email notification. So, if you combine all these building blocks, then you get to see the setup of our project. As you see in the upper one, that's the internet, the global one. Then we've got a Honeywall. It's a standard setup nowadays. And then there are several honeypots. For example, we have one Solaris machine. Then we have one machine for testing purposes where we play around with different systems. And to keep the hardware requirements low, we use mainly virtual machines under VMware. So we have several older Linux versions, several older BSDs running, and these are just virtual machines. And then there's also this HoneyD. HoneyD is a kind of virtualization of the TCP IP stack. It just fools Nmap, Xprobe, and all other tools. It's basically for collecting quantitative information about attackers. So nobody can compromise these. These are just virtual systems and just for collecting statistical data. Are there some questions about honeypots, or should I continue now with Nosebreak? Okay, one question?
Are you using live Linux installations then on your VMware, or are you running like a dummy software that just simulates a live system?
These are normal installations. So we run a Red Hat 7.3, a Red Hat 9, and Fedora ones. So basic installations without changing much, just installing CBAC so that everything is logged and not more. On the HoneyDs, there are scripts that simulate services. Okay, Nosebreak. We are running our HoneyNet since February this year, and unfortunately we had no successful compromise yet. I don't know why. Probably all the crackers outside in the world are too stupid to compromise one of my machines. I think it's not that hard, because for Red Hat 7.3 there are at least 50 known exploits, probably more than 100, and they are just too stupid probably. So we thought, okay, then we turn the table and we attack our own honeypots. And the outcome is our toolkit, or the project Nosebreak and the toolkit Keybase. We wrote also an academic paper. I think it's in the proceedings, and you can get it at the archive. We also did a short presentation at Black Hat about this, and now I want to give a brief overview of what we did. I don't have that much time, so I have to skip some parts, but if you are interested in this, read the paper, then you get all the information. This is an excerpt of a paper, one of those Know Your Enemy papers that are published on the official HoneyNet site. It describes how CBAC works, and as you see, I have made some of those statements in red because we show that these are not true. So it's not true that CBAC has the monitoring capability to log all activity on a honeypot. And in the lower part, the author claimed that once that it is possible to disable CBAC, but during the disabling, everything is logged, and this is also not true. So we can bypass, circumvent, and also disable CBAC, as I'll show you in the next 30 minutes or so. At first, a brief introduction of what CBAC does. So I have said before that it's basically just a logging tool. And then the first part, I'll concentrate on the Linux version, on the Linux 2.1.7. It's currently the official version. And in the later part, I also take a look at CBAC at other architectures. They all do the same because they all have the same logging format, the same techniques basically. So the results that I present in the first part are also, you can also use this on other architectures. Okay, so what does CBAC do? At first, it hijacks the system read call, so it's like a rootkit. In the previous version, so in very early versions, it was based on a door by Stealth. I think Stealth is not here, but his rootkit, it's the basic of CBAC. But afterwards, the maintainer of CBAC decided that a door has too much power for the things he wants to do, so he doesn't want to hide processes or similar things. So he started from scratch, and the outcome is now CBAC in the current second version. Except from hijacking the suite, it also does some kind of logging, as I said. So it creates some Ethernet frames, and it directly communicates with the Ethernet driver to transfer those Ethernet frames to the logging server, so to hide the communication, to make it more stealth, so via direct communication with the driver. If you've got a tool like TCP dump running on a honeypot, you don't see that there's some logging going on, that there are packets that go outside of your system, so basically just to hide its presence. And it also has to override some parts of the network stack because it communicates with the network driver, but the network driver itself does keep track of the counters, and it has to adjust the counters before these are displayed. So there's also some modifications on the network stack for Linux. CBAC, like I said before, like a rootkit, it also wants to hide its presence. That's true because if you compromise a honeypot, do an ls mod and see that there's something fancy logging all your activities, probably you also log out immediately because probably you don't want to get traced while you hack some systems. So it uses the technique that also Adore itself uses. There's this cleaner.o, it's part of Adore and Adore Next Generation. It basically just unlinks the last module from the list of loaded modules, so it does just one pointer instruction basically. This works because the kernel itself has a module list. Inside this module list, the kernel keeps track in a linear list of which modules are loaded, and via one pointer modification, you can just unlink it, and then you remove cleaner O itself. So the kernel hasn't CBAC itself in the list of loaded modules, and so lsmod and all other tools don't see that there's another module loaded. Okay, this should be enough to understand what CBAC does, and now we take it 5 different approaches how to detect CBAC itself. At first, we take a look at latency, and afterwards at some other things. Currently, I only have one notebook here, and if you do a presentation, everything goes wrong. So I have some movies. The movies show what we did, and the movies ensure that nothing can go wrong for me now. The setup is depicted in the lower part of this. You see the attacker. The attacker, he has compromised one of the honeypots behind also a honey wall. He has got an SSH connection inside, and we take a look mostly at what what's happening at the honey wall within the movies. Because we've got this SSH connections, about 1 kilobyte of data are transmitted per second between both endpoints. And so if we've got something like ifconfig running, then there's an incrementation every second or so. Okay, the first one, how to detect CVAC just via latency. If you just use DD, so a very easy tool, and you just copy from def0 to def null with a block size of 1, you can basically copy more than 1 million blocks per second, and CVAC has to log all those 1 million read calls per second also, and because CVAC is not that fast, you can see some latency. So hopefully the movie works. Yeah. Shit. Okay. Angel. Okay, then sorry. Then I can try it again. Probably the resolution is too high for this beamer. Fuck. Sorry for this inconvenience. I have also already problems with this notebook. So, I think this shouldn't look like this. Okay, then I doubt that we don't have any movie now. Okay, I can try this, yeah. Okay, it doesn't seem to work. I can. Okay, so sorry. On my laptop, these movies. Sorry. My mouse pointer is also not. Okay, cool. Okay, at first we take some snapshot of the latency that's currently inside of the network. So we just ping, the default gateway. You see that the latency is about 0.3 milliseconds. So now we start this DD in the background. We copy from def0 to def null. That allows us to copy very, very fast because you just copy via devices, and with DD it's very easy. So we do some kind of denial of service attack against CBAC itself because we just do that much. Currently the film runs and runs and runs. As you see, there's nothing happen because the SSH connections basically hangs. In a few seconds this latency should go away and you should see that the typing starts again. Let's see. Okay, there it's again, and as you see, the latency goes up at about 2 seconds, and we also got a packet loss. So now we've got high latency inside the network because CBAC tries to send as much logging packets out as it can, and of course there's only a limited capability, and you can see this latency just via ping and DD. Okay, next one. As I said before, CBAC also has to modify this, the network counters because it communicates directly with the driver, and the driver itself adjusts all counters. So it has to assure that before the counters are displayed to some other program or so, these are adjusted again to the values without the packets that were sent by CBAC itself. So if you just write a kernel module, load this, and the kernel module just stops those modifications, then you see that there's something fancy going on. Another movie of this one, DefChecker. So DefChecker is basically a very easy kernel module that does just adjust the pointers as they should be in a real kernel. In the upper part, you see that an fconfig output every 1 second. You see due to the SSH connection inside that the TX counters are going up a bit per second. Then we copy 1 million bytes from def0 to def1, and as you expect, nothing happens at the TX counters. If you now take a look at the TX counters again, after we loaded the module, you see that the TX pointers jumped from 130 kilobyte to more than 76 megabyte. And if we start now the DD again, then you see that per second about 1 megabyte is transmitted. So we are now at about 79 megabytes, and if we now remove the module again, so via mmod, then the pointer, the TX counter magically jumps again. Sorry for the typo. Jumps again back to 147 kilobyte. So you can modify. You can see that there's somebody playing around with your counters of your network stack. Oh yeah. I hope you can read it, probably not the people in the back, but probably the people in the front. What is not correct at this picture? Okay, as you probably see, the TX counter is about 4 gigabyte, and the uptime is 4 minutes. So if I had this big pipe, so 1 gigabyte per minute, then I wouldn't sit here probably. These are strange things that happen sometimes. There are also this adjustment of the counters doesn't work as it should. As you see, we've got this overflow in the direction, and therefore the TX counter was at about 4 gigabyte. So the handling of the send packets is not easy because CBAC doesn't correctly log everything what should be logged. So there are some fancy things I see when I do this kind of stuff. Then let's see. I think I have half an hour, so the excursus is very short. Just to give you an overview of how system calls look like, probably most of you know how these look like, so this is very, very brief. In Linux, we've got this user land and this kernel land. User land is where all processes do that kind of stuff, and kernel land is where the kernel itself does it. As an attacker, you want to be in kernel land because there you have got basically no limits. You can do whatever you want. But because most people don't like what you do there, the kernel has some traps where you can enter from user land to kernel land, and normally you can't do anything else. So the trap from user land to kernel land looks like this. If you call in one of your user land programs the read system calls, then basically the parameters are pushed on the registers of the processor, and via the call of 0x80, so hex 80, this is the trap between user land and kernel land. In kernel land, the kernel at first takes a look at what he should do. He searches in the IDT in the interrupt descriptor table of what this interrupt should do, this hex 80, and it sees, okay, I want to do a system call now. So afterward, it takes a look at the system call table, SDT, what to do. It sees in the registers of the processor, okay, I should do a read call, okay, and then it does this read. So at first you put everything in the registers, then you do the interrupt, and after the interrupt is handled, the processor does whatever you want it to do. The system calls are all defined in this file. I've listed the first three. Exit has number 1, fork 2, read 3, write 4, and so on. Linux, as a monolithic kernel, has about 250 system calls currently. As an attacker, probably you want to modify the system call table so that the system calls do what you want to do. This is mainly the techniques that Adore uses, so modifying the system call table as a rootkit. This is the way to go, probably. The system call table itself is just an array, and the array is an array of pointers to functions. So, for example, at the entry syscall table, at the NR open, then there's a pointer that tells the kernel how to handle an open call. This is all in kernel space, so the pointers are from within the system call table to somewhere in kernel space, and there the kernel sees, okay, when someone calls open, I should do this and this. So if you just override this pointer in the SDT, then you can do whatever you want. So you override the pointer to your hacked sysopen. Within this hacked sysopen, you can do whatever you want, and this is basically the techniques that rootkits use. In 2.4 until recently, it was very easy to get the system call table, and then for security requirements, so the kernel developers don't want you to mess up with your system call tables, they stopped exporting it, so it's not that easy now. But you can do this kind of stuff with this code snippet. You can get the system call table. This works on most 2.4 and 2.6 kernels. Unfortunately, it doesn't work on Fedora Core 2 and 3 because they don't export the necessary symbols. But there are always ways to get your system call table, for example, via fingerprinting or this kind of stuff. Okay, so modifying of the system call table, that's what rootkits does, and this is also what CBAC does. CBAC just overrides the sysread call, and within the overwritten function, it does all the logging. It creates an XEMIT packet, and this packet is handled to the driver, and the driver sends it out, and this is what's done in the hacked version of the sysread. But because it overrides the pointer, you see that there's something going on if you take a look at all pointers in the system call table. Before loading CBAC, the system calls of sysread and syswrite are very near to each other because they are also near to each other within the definition and in the header files. And afterwards, after you load CVEC on a host, you see that the system read call points to a totally different memory location. So via kernel module, you get all the pointers, you just compare those, and then you see that someone modified your system call table. This can also be used to detect rootkits, of course. So now we've seen 3 ways, 2 more to go. One is about how to find hidden modules, and the other one is what else can be done in memory if you just take a look around. If you take a look at the header files, then you see that these have some characteristic entries. In the back I have got this from a recent 2.4 kernel. They didn't change much inside the header files lately. Only the 2.6 version changed. So the whole module handling is completely rewritten and not that nice, I think, but okay, we have to live with what we have. So this is just for kernel 2.4, but this technique can also be used on 2.6 kernels. If you take a look at all these pointers, at all these variables that are depicted in this picture, then these are all pointers either within kernel memory or within the module itself. So all those pointers only have a very limited range. If you take a look at other variables within the module structure, there are also other variables that have only a very small, reasonable range. For example, the size is always 96. The use count is most of the times under 5, so between 0 and 5. The flags and the number of dependencies on all this also have a very small, reasonable range. So mainly you can do some kind of heuristic to find inside memory what looks like a module. We implemented this technique, but afterwards we found out that in a recent Frack magazine there was some article about how to find modules. It was in the line noise section, and this does basically the same like our code does, but this is the code from the Frack article, so you can just read what they have written. It's much nicer because we didn't write anything on it. We have just the code. It works basically like this. If you've got vmalloc, this is used inside kernel. This is used to allocate virtual memory, and this memory is always aligned to 4K on a normal IA32 processor. So if you call an vmalloc, then you always got at least 4Ks, and the alignment is always in 4K steps. The memory allocation always starts at vmalloc starts and ends at vmalloc reserve. So you can just do some kind of brute forcing. So you start at vmalloc start, go for search for characteristic values. So you do a heuristic, then go 4K forward, start the heuristic again. So you just take a look at around what looks like a symbol, what looks like a module, and it's very efficient, as we see in the movie. Module Hunter is the tool that's used. So at first we take a look at via lsmod of what the kernel thinks, what modules are loaded. Then we just load the module hunter itself. Module hunter itself has no nice interface. It's just via proc show modules, and afterwards you can via dmessage see what the output of module hunter was. So if you compare now the output of module hunter with the output of lsmod, you see that most of the modules are also displayed via lsmod. In the lower part there's also the module hunter, of course, because we loaded it. And if you compare it, you see that this sound-pcmcia is new, so this is hidden via before lsmod. So this is some fancy kernel module, and in our case it's CVEC. Okay, and once we know that there's a hidden module, we do the heuristic further, and so we can also reconstruct the critical values that are used by CBAC. CBAC uses a fancy technique to hide the parameters that are given. At first, it generates a randomized a memory field with all nulls inside. So we've got one large block with all null values, and then randomized all parameters are also added to this memory block. For example, the magic number that's used to verify that this is a correct CBAC packet, and also the port number that the CBAC packet should be sent to, the IP address of the logging server, and some other config variables. If you fill in, the memory layout looks like this, and after each compiling, it's new because everything is randomized, the length, the position, and everything else. Okay, now you can start some kind of heuristic if you know where this memory block starts. For example, if you take a look at the value in red and translate it to an IP address, it's within the 240 range. 240 is a reserved space, so this is probably not the IP address of the destination where the CBAC packet should be sent to, but this could be, for example, the magic number. If you go a step further, you can, for example, translate this value to an IP address. This could be also the magic number, but this looks more like an IP address. You can do the heuristic more again. This could be, for example, the magic number. This could also be the port number. Who knows? But we have only got a heuristic. So, so nosebreaker in action looks like this. Right. Nosebreaker itself is written in Python, so easy to start. We stop it, the movie here. At first it retrieves the system call table, verifies that some things are like they should be, and then it sees that the sysread and the syswrite system call are not as they should be, they are not near to each other, and okay, the message there is wrong because not syswrite but sysread is hijacked. But as explained before, via just looking at the addresses of the system call tables, you see that there were some modifications. And if it sees that someone modified the system call table, it starts its heuristics. This is the output. Now it should. Okay, let's see. We have now in the lower part, this is the config file of CBAC that we need. And in the upper part, we've got the output of nosebreaker. So if you take a look at the possible IPs, you see that the destination IP is 10, 11, 12, 1. If you take a look at the list, these are about 20 values. So the heuristic gave us about 20 IP addresses, and this destination IP address is already the second one. There are also some others that you can exclude, but instead of having to test all 2 to the power of 32 IP addresses for the destination address, you've got only 20, and so you've got a big reduction. Also, for example, the magic number, the magic value in the lower part, if you translate it to hex, there's also the stat beef. Yeah, it's in the second line, the fourth last. So it also was able to reconstruct the magic value and everything else. In the lower line, you also see it was able to reconstruct the memory address of the init and the cleanup function, and we can do some more stuff with this one. So we also have got the init, the address of the init and the cleanup function of the module. This helps us also to disable CBAC itself. It's very nice because if we just call cleanup, CBAC is very nice and just disables itself. So we just write a kernel module, we give it the address of the cleanup functions. The kernel module just jumps to this memory location and calls the code, and CBAC, as kind as it is, it unloads itself. So we just have to tell, please unload yourself, and it does it. Thank you. The obvious way to disable CBAC on a running kernel is by just disabling it. So you reconstruct the pointer in the system call table, and then you are also done, because if you reconstruct the pointer, then CBAC and the sysread call is as it should be, and no logging is taking place. And there's also the crazy way. If you just patch in your own untainted version of the system read call, then you're also able to bypass all logging. But this is not that easy, because you have to generate all the shellcode and patch it inline. We haven't tested it, but it should work. Okay, now we take a closer look at Keybase, the other tool that we wrote. If you take a look at what can be logged, so if you're running a honeypot and if someone compromises your honeypot, what information do you have? Of course, you've got all communication traffic. This is because there's a honey wall in between. It logs everything, all traffic, and you can't do anything against it. Of course, you can do something, just use encryption, because without the appropriate key, the operator can log whatever you want. It's useless for him. All calls to read are also logged before we disable CBAC, so we should find a way to avoid calling read. And after a break-in, if we compromise the system, eventually the operator will notice this, so we should also keep everything in memory so that we don't leave any traces on disk, and we should avoid also this log and everything, so leave as less traces as you can. If you take a look at who needs read, of course all interactive programs use read, because they have to read character for character, but almost all other programs also need read to read in config files or similar stuff. Network programs are another thing, because they usually use receive, and receive isn't logged this way. One way to make or to circumvent CBAC would be to make the logging unreliable, so we can do this DD attack again and hope that the denial of service against CBAC helps, and some packets, some of our actions are also discarded, but we can't control what happens, so this is not reliable, so we need another way. And the other way is by just using mmap. We can, instead of using read, we just map everything as we want. So we leave all the kernel alone and map whatever we want inside memory, and so we don't have to call read. There are some limitations. We can't map everything what's under def. We can't use pipes and similar stuff. And def random would be nice to have some crypto for generating our keys that we need later for the communication channel. But then we need to find another way to generate our crypto seeds. And the nice thing is that the logging of everything what's mapped inside memory is very hard. Probably it's not possible at all, because I can just map 2 gigabytes into memory, and and I want to see how CBAC translates those 2 gigabytes to another system. To make this mmap thing nicer, you can also talk directly with the network. You execute the commands directly. There's a nice paper written by the Krug in the latest Threck issue, who also does this kind of stuff. And the nice bonus is that if we call exec itself doesn't call any reads, so we can also execute whatever we want without calling read. The drawback is that if we exec something, then it could be that a library is loaded, and the library could also load other libraries, and we can't control these read calls. So the loading of libraries can't be completely be circumvented. Other stuff is that we can just play with a process name. We copy things from one part to another part, execute it. This is our only things to make the life of a forensic much harder. So we just play around. There are some scripts that do this in an automated fashion. This is just to make forensic hard. If you combine all these things, then you got Keybase. Keybase is a toolkit written completely in Python for easy developing. It can do everything you expect from basic shell, so you can execute things, you can read, write, you can change directories, you can display things, and everything what you can also do with the basic shell. It's highly dynamic. It keeps everything in memory. If it has to write something on disk, it has also the capability to securely delete everything afterwards via 7 times writing everything with nulls and this kind of stuff. And therefore it doesn't leave much traces on a host itself. There are several layers. The lowest layer is the network layer. Basically, it uses now TCP sockets for networking, but it could also use other things, so you can communicate with everything you want. On top of this network, this TCP connection, it implements Diffie-Hellman, and with IAS, it also has random padding, so we have got a secure channel on top of this TCP connection. We get the seed by having some thread traces and high resolution timers and this kind of stuff to get some crypto seeds. We know that this is not perfect, and Diffie-Hellman is also not prone against man-in-the-middle attacks, but this is okay for our use case now. On top of this IAS layer, there's the so-called KBIS layer. The KBIS layer is designed to be asynchronous in the current version because it's only proof of concept. It's only synchronous, so you send a command and get the reply back later. You can also send several commands at once and get the replies back later. The nice thing is that it's very high dynamic, so you keep everything in memory. At first you just send the server to the Honeypot. The server initially only knows one command, and this is the add command. And afterwards, all other commands are sent via Python modules to the server. These are loaded into the server itself. So at first, it only knows the command to add other things, and then you can load during runtime new versions, new commands inside the memory itself. So you keep everything in memory. You don't have to write anything to disk. And so, yeah, you don't leave much traces. Yeah, as I said before, we push everything from the client to the server. The server is, during runtime, it gets more and more commands, and everything via serialized Python objects. The implemented commands currently are reading, writing of files, the secure deletion via continuous overwriting, the direct execution of commands, listing directories, and other stuff. Okay, I think I've got only 5 minutes left, so just the securing. Sorry, the securing. So how to secure it? There's a version I've written. I can't release it currently because there are some issues, because the HoneyNet org people also want this version first, and there's some quality assurance going on. But another thing is you just don't fill everything with 0 byte. You fill it with random data to make this complete heuristic, error-prone. Other things would be the disabling of loading of modules. Once CBAC is loaded, you can do this via capabilities in Linux very efficiently. Also, some rate limiting and thresholding is thought about. It's not currently implemented, but will be probably in a later version. And the best solution would be probably a kernel patch. I started writing it. It's not currently finished, but on my to-do list. If someone here is interested in helping this, just contact me. Okay, then just 5 minutes. I just want to do this 3 slides now. On Windows 32, the same as possible. There was someone from Hong Kong who did the same techniques for Windows. He basically uses the techniques we used, and it's basically on the other architecture. For NetBSD, it's also possible. They use somehow other techniques to modify the system call table. They avoid it by just jumping as a first instruction to the hacked value, but this can also be detected. There's also a paper from the French HoneyNet people, and also the OpenBSD version is error-prone. Okay, then thanks a lot for this part, and the other parts and the slides will be online at the CCC site, I think, or I can put them on my site. And now I'm open for questions. Thanks a lot. Okay, no question.
One question, or perhaps one idea. Filling the zero fields with purely random data leaves some small skew in the distribution. So I would either use a biased random source or build a pseudo-random sequence which I mix in the fields so that the distribution is really equal. Otherwise you get some peaks, and this could be used in the same manner you extracted it from the null field.
Probably yes. Yeah.